First of all, I want to say thank you very much for everyone who's attending today and being involved in our AccuLase GPA presentation. This is a launch of a new analyzer in our portfolio, and we're really excited to have you here to discuss the features, benefits, advantages, and the value. So without further ado, my name is Ian Tell. I'm the VP of Sales and Marketing, and I'm here to introduce the AccuLase, our latest platform in H2S measurement and a number of other things as well. So it's our latest version of the process gas analyzer. It's a tunable diode laser absorption spectroscopy analyzer, which is there to measure H2S, CO2, and H2O all in a single analyzer. Really, the key here, more than anything else, is 3 measurements, 3 compounds, 1 cell, total certainty. So everything is done in 1 cell in 1 measurement. And we're going to talk a lot more about the value of being able to do it that way. Again, Galvanic, this is our 6th H2S platform and our overall portfolio. We have a lot of experience here, and this is just another development in our expertise in making sure that you get the right measurement for your application. So when we take a look at the AccuLase as a whole, here's the key features, benefits, advantages, values of the analyzer. As I mentioned before, 3 compounds, 1 cell, total certainty. So everything is done inside a single cell. 1 Harriet cell, so not multiple pieces of hardware. Makes it very simple and clean and easy for a smaller footprint and easier design. No scrubber, therefore it's a direct measurement, not a subtractive measurement or implied measurement, and also allows for quicker measurement and a lack of consumables in the overall measurement. The low range sensitivity is the best on the market from an LDL point of view for lasers, which is 0.15 ppm for H2S. And it has the ability to be multi-stream. So we can do up to 4 streams in a single analyzer. So all of these things really equate to lower maintenance, higher reliability. When we take a look at the market side of things, really this analyzer, the reason you're here is because we designed this for you. We designed the analyzer to take a look at the specific markets you're in, whether it's refinery or natural gas or biogas, and really looked and listened to the market in terms of what they liked about laser technology, what they liked about how it works, but some of the complications and some of the things that they wanted to see fixed overall in terms of how the measurement is done and the reliability of the side of things. So really the analyzer was designed with the end user in mind to make sure we were going to create the certainty that's required in your H2S measurement, including CO2 and H2O as well. So without further ado, I'm going to turn the floor over to Parisa, who is our Senior Portfolio Manager. She's going to talk to you about the technology, measurements, design, operation, and maintenance of the analyzer.
My name is Parisa. I'm the Senior Portfolio Manager with Galvanic, and today I'm going to start with a quick overview about how TDL, or Tunable Diode Laser, works. I'm also going to discuss the analyzer design, specifically what is the design behind the AccuLase, the operations, the measurement, as well as the maintenance key points, which are the main features of this analyzer. On the left side here, what you see is the laser launcher, the cell window, the detector. Underneath the cell, the Harriet cell here, you see different parts. What they are is the laser source, the heater, the pressure transducer, as well as the vacuum pump. Now, in order to make the measurement in our laser, the specific wavelength of the light that is emitted by the laser is controlled by adjusting the current as well as the temperature of the laser emitter. So the light basically goes through the laser launcher, it gets focused in here and the laser launcher side, and then after that passes through the cell window and then all the way through this Harriet cell. So the cell that we used here is called the Harriet cell. There are 2 mirrors at both ends of the cell, which are basically used to increase the overall path length. And the way they do it is just basically by reflecting the laser light back and forth, many, many times in this cell. Therefore, when we do that, when we repeat that, then the higher, the more time we do it, then the higher absorbance will be obtained. In this case, the length of the cell that we are using is 52.6 centimeter. The laser is passing through the cell 100 times. Therefore, what we get at the end is 52.6 meters for the overall path length. So at the end, the light exits the cell, it just gets detected by the detector, and finally, the concentration of what we are measuring can be calculated just using the Beer-Lambert law, simple spectroscopy. All right. Another point to consider is that we are actually using sulfonert for the low H2S applications because it is more inert to absorb H2S than stainless steel and some other materials. Therefore, it reassures a very good sample integrity and a good measurement at that. So here is another view of the cell. Basically, what it shows is where the mirrors are located at both ends of the cell. So it's a very simple and robust design to work with, easy to maintain, easy to clean. And later on during the demo, Dave will show us exactly how that looks like and how easy it is to work with the cell and maintain it particularly. All right. So for the analysis, what happens is that we start by obviously extracting the sample or the gas using a sample probe. Then we filter that sample for any particulates or any liquids to make sure that we get rid of those. The pressure gets regulated. The sample passes through the cell, which I just showed you. The H2S absorbs that light. And from that absorbance, again, the analyzer can calculate what is the concentration of the H2S. Same thing, of course, applies to any other component we are interested to measure here. Now, on the right side, you see that graph. This basically shows you the absorption spectra for different species. That includes H2S as well. That's in the background of other gases, obviously. For example, CO2, moisture, depending on the stream, other things. So although interference species might exist in the stream, the way we do the analysis and the way our laser works is we use the vacuum pump in our system. The whole idea is to make sure that we keep a partial vacuum pressure in the cell. So we are able to isolate the line that is of our interest, in this case here, this red one here for the measurement, without worrying really about what else is going on in terms of the other species. So we isolate that line, there is no interference from any other component. And this is obviously how the pump looks like. Another main advantage of using the vacuum pump is that we're actually not using any scrubber, any other consumable in our design, in our AccuLase, which is another benefit and advantage of using the vacuum pump. All right. In order to improve the sensitivity of our analyzer, we're also using a fairly common feature that is called wavelength modulation spectroscopy, or WMS. It is based on the modulation of the light emitted by the laser that is slowly tuned through an absorption feature of the species that we are going to detect. So the interaction of the modulated light with absorption light can generate signals at different harmonics of the modulation frequency, which we can use them for the analysis. So the whole idea, without going too much to the detail, is that at the end of the day, using the wavelength modulation spectroscopy, we can get a very good signal to the noise ratio. So we can increase that, the signal to the noise ratio. And that combined with the other designs and features of our system, for example, the vacuum pump, as well as the line Harriet cell, that gives us the opportunity to be able to do a very good low detection limit measurement with a great accuracy. This one here is a nice summary, just basically showing the main measurements of our AccuLase. We can measure all three components, as Ian mentioned, and just one single unit, one single cell. For example, for the natural gas value chain, we can do the H2S 0 to 500 ppm with an LDL of 0.15 ppm. For the moisture, we can do 0 to 500 ppm. LDL is 5 ppm here. For the CO2, we can do 0 to 5% with an LDL of 500 ppm. Again, everything is one single unit, one single cell. Other ranges obviously can be offered as well, just depending on the application at the time to review them. AccuLase can also support multi-stream measurements for all these components just using the same unit, which is another advantage and a good feature about this product. Okay, this one here just summarizes very quickly some information regarding the enclosure design, the materials, the dimensions, as well as some utilities required for this analyzer. Certifications of our interest are for the North America, obviously Class 1 Deep 1 and Class 1 Deep 2. For the international, it's ATEX, ICX, Zone 1 and Zone 2. So we have considered all of those to make sure that we can serve all the applications internationally, all around the world, basically. Okay. So here you see just another view of the AccuLase Design. So basically, we can offer a variety of user connections, IOs, as well as communication options. This analyzer can support 4 to 20 milliamp analog output, discrete inputs, dry contact relays for concentration, as well as the fault alarms. We have Ethernet for Modbus, TCP/IP. We have Ethernet for remote GUI, as well as Modbus RS-485, Modbus RS-232. So lots of features and options are available here. The system also is sealed from the environment for corrosion protection. It uses epoxy coated components as well for that purpose. You can see the laser assembly, the cell, the heater, the vacuum pump, as well as all other components for the sample conditioning system on this side. For example, the membrane filter, as well as the pressure regulator. The system, as you see, is really space saving. It's very simple and robust. Again, everything the same thing as we said a few times here. So one sample cell, very good for maintenance, so you don't have to worry about 2 cells and lots more to deal with when it comes to maintenance. Also, same maintenance requirements again for all the units and models. Easy to deal with. Okay, so the front panel of the control enclosure also includes a color display, which basically provides information about the status of the analyzer, about concentrations of what we are measuring, cell temperature, pressure, and much more. In addition, there is a handheld keypad with this system that can be used to view or edit the settings as required. So once we do the demo, Dave is going to walk us through the main features of the display, the keypad and all that, and you'll see how they look like and how they work. These can also support the remote access, which is an important feature for a lot of clients. So that's done through the web-based graphical user interface or just web-based GUI. This allows the user to view the analyzer results, also to configure basically analyzer configurations, to carry out manual analysis as required. The beauty of this GUI is that it's accessible through an internet browser software such as Google Chrome or Firefox, so no specific software is required for that. It can also work simply by just connecting the analyzer and typing in the IP address of that analyzer. Then you'll just basically see all the information that is available. The GUI can also operate on a local area network or just simply through the direct connection of the analyzer and the PC, and that's it. All right, so this one here is a view of how the sample conditioning system looks like for the AccuLase. The whole idea is to make sure a really nice, dry, clean, and particulate or liquid-free sample goes to the analyzer for analysis. The sample conditioning system in AccuLase includes switching valves, obviously, to switch between different streams, as well as between sample and the calibration gas. The pressure regulator is another part of the sample conditioning system. Also, a liquid membrane separator, just another component that comes with a sample conditioning system. Other techniques, such as using a genie probe membrane, can also be offered. Just basically the way it works is to insert that probe directly into the pipeline to separate all the liquids and particulates from the gas, and then just send it all the way to the analyzer. So the point of no matter what we do here, the point here is to make sure at the end of the day, a really nice and clean and dry sample goes to the analyzer for analysis. All right, so another question we get often is that what is the maintenance requirements for this analyzer? So AccuLase is a very, very low maintenance analyzer. It does not have any consumables, as I mentioned, so that's a very good feature. We recommend monthly automated calibration for this unit. The only maintenance really with this analyzer is just replacing the membrane filters every quarter if required, if there is any leak, for example, and also the vacuum pump diaphragm annually. So it's very easy to do any of those. It is very, very, in terms of the cost, very low. And again, just takes a few minutes, and that's pretty much it. Dave, again, will walk us through some of those, and we'll mention more about the maintenance and how easy it is during the demo session. So again, this analyzer, very low maintenance, a long-term investment. Nothing to worry about in terms of the maintenance with this one. All right, so as I mentioned earlier, the system is certified for a variety of hazardous array classifications. This one here is how the DIV2 unit looks like. You see the sample conditioning system on the right side. You'll see the Harriet cell as well. You see all the optic cell components in this enclosure. Size and design very easy and accessible to work with. Different components, as we mentioned before, all included in this little unit here. This one here is the view of the DIV1 unit. Again, on the right side, you'll see the whole sample conditioning system. Optics and sample cell enclosure all insulated for the heat integrity purposes, as you see here. Obviously, you see a lot more about other details and other components of this system, which I'm not going to repeat again, but you'll get a chance to see them in the live demo as well. All right, so this was basically an overall overview about all the main components, the features of this system, which you'll see during the demo. At this point, I'm gonna pass it on to Ian again to discuss some of the benefits and advantages of this unit. Ian?
Thank you, Parisa. So I'm just going to go into a quick summary of what Parisa specifically talked about. So again, key elements here: 3 compounds, 1 cell, total certainty. 1 Harriet cell means that you have reduced analyzer hardware, which makes it much more compact and easy to use and easy to maintain. No scrubber, therefore you don't have to worry about consumables, and you're not looking at a subtractive type of measurement. It also creates maximum uptime. Low level detection limit for the H2S. No consumables, as we mentioned, and the ability to have multiple streams. So again, really it's all about making it as compact and easy and reliable as possible in a single unit by having those 3 compounds in 1 cell for the overall measurement of everything. So you're not here to listen to me necessarily. You're here to actually see the unit and how it works and how easy it is.
My name is Dave Height. As Ian mentioned, I'm the Director of Product Development here at Galvanic. And we're here to show you our latest analyzer that we've just recently released. So what you're looking at here on your screen is the Class 1 Division 1 version of the analyzer. Parisa showed you some pictures of the Class 1 Division 2 as well. And the concept of the 2 analyzers is very similar. We have basically 2 enclosures. The upper one is containing the electronics that operates the system and has all the customer inputs and outputs. And then we have another separate enclosure that contains the laser itself, the gas cell, the vacuum pump, all the things that are required to actually make the measurement. So if we have a little bit of a closer look at the upper enclosure, we can kind of see what's inside. So we have on the door is a controller. This controller basically does all the computations necessary to generate the concentrations of gases that we're looking at. Also located there are some Ethernet ports as well as some USB ports. The Ethernet ports here, there's 3 of them. 2 of them are dedicated for network access, so you can actually have plug it into 2 different networks. The 3rd one is dedicated to a local Ethernet connection so that you can plug an Ethernet cable directly into a laptop. The analyzer has a dummy IP address that you can type in and communicate with it that way. That port is accessed through the front panel. It may be difficult to see. This display is a little bit too bright for the webcam, but if you open the explosion-proof window, you can actually access that Ethernet hub without having to open the enclosure. So also located inside, this is the main board in the back here. This is where all of the inputs and outputs are handled. So for example, along the side here, we have all the inputs associated with measuring the pressure and temperature of the laser. Along the bottom are the customer outputs. So there's 4 analog outputs here. There's 4 relay outputs here that are configurable for fault alarms or concentration alarms. And then we have some solenoid drivers along the side here that are used for switching solenoids for stream switching, calibrations, and things of that nature. Power comes in through the top. There's power connection is right here. This is an internal power supply that provides 24 volts to the rest of the system. So in terms of the user interface, the local user interface, again, I do apologize for the inability to see that screen very well, but basically what it shows you on the home page is the concentrations of your gases, the pressure and temperature of the cell. These are important things that you would want to look at. And then it has a scrolling system through a keypad where you can use page scrolling to look at alarms, the status of various outputs, do your calibrations or validation checks, look at some of the parameters associated with the laser, do a little bit of configuration. So basically, the local user interface, the concept behind it is to be able to do most of the basic things that you would need to do for regular maintenance and regular operation without having to drag out a laptop. So physically, a few things to point out. Along the side here, the gas entries are here. So we have the sample gas that's going through the membrane filter. We're using a Genie 123 membrane. There's an option for a fast loop here that you can use by opening the sweep from the Genie. That serves 2 purposes. One is to ensure that you've have representative sample at the analyzer at all times. Also, if any liquids fall out, they can be swept away. We go into a pressure regulator. We regulate the gas to 10 pounds per square inch gauge. There's a 3-way valve. In this case, it's a manual valve that can be used to introduce calibration gas. Optionally, we can have a solenoid valve to do that same function. Gas then flows into the cell. This is a metering valve here. And then here's the vents that the gas exits the cell to the vent. So this metering valve here is used to balance the pressure in the cell as well as the flow. That flow is typically between 2 and 3 liters a minute, and it exits out of this out of the vent line here. Typically, you would vent that either to atmosphere, or you could also send it out to a low pressure flare. We can pump against on the order of 2 or 3 psi. So if you do have a low pressure flare on site, we can pump the effluent from the cell into that. So again, at the bottom enclosure, it's temperature controlled. It's got this insulated blanket on it just to help keep the temperature controlled to 40 degrees Celsius. But to actually see what's inside this lower enclosure, I'm just going to swing my camera around a little bit. The components that are inside the lower explosion-proof housing, are on a rail. This entire rail is accessible. The end caps of that explosion-proof housing screw off, and there's basically 2 bolts that hold the rail in place. You undo a couple of the gas fittings. The electrical can be undone by just simply pulling the terminal blocks out of this little connector here. And the whole thing comes loose. You can pull it out, put it on the bench. If you're working with a Div 2 unit, you do have similar access to this, but it's not all on one piece. So you would remove the cell separately and remove the vacuum pump separately, but you do have full access to those components. So on the rail, we have a heater that's basically a contact heater. It just kind of heats everything that's in contact with it. Gives a nice stable thermal environment for the optics. We have the laser driver board here. This basically generates the laser signal. So the laser itself is actually attached to this board on the bottom side. It's a fiberized connector. So you see this fiber optic cable here carries the laser output into the laser launcher, launches into the cell, goes through its 100 bounces, eventually pops back out, lands on this little mirror, and then hits the detector. And if your gas of interest is in the cell, of course, you get some absorbance and it makes a measurement. So to talk a little bit about, just touch on some of the maintenance items associated with the analyzer. Parisa mentioned the Genie filter. Typically on a quarterly basis, you may have PM schedules that you look at your sample conditioning a little bit more often than that, or maybe not. It's kind of up to you, but we recommend at least quarterly. So the maintenance on these items is relatively simple. It has a screw-off cap, so when it's all done up, you can use a screwdriver or something along those lines to pry open the device. It just simply screws apart and gives you access to the membrane. Now this, I'm doing this on the bench, but there's no reason to unmount it from the analyzer panel. This can basically be done in situ. So basically you can see that this one's been in service for a little while, so you see some discoloration of the membrane. It's usually white. In fact, inside the body of the cell, you can see some oily material there. So this filter has been doing its job. It's taking out some oily material, preventing it from going into the cell. So basically, you would clean that out with some solvent. You can use a small screwdriver or an O-ring pick to take this O-ring out. The membrane simply comes off. A replacement kit, which contains the membrane and the O-rings, is available. You just simply replace the membrane, the O-rings, the whole device screws back together, and you can simply put it back in service. So that's the filter itself. Now we talked about some annual maintenance requirements for the vacuum pump. So the vacuum pump is here. I will mention that it's not necessary to take the whole rail out if you want to work on the vacuum pump. You can simply slide it out of the explosion-proof enclosure just far enough to give you access to the pump, because basically what you need to do to service the pump, and I'm actually going to take it off the rail here just to give you a little bit of a closer look at it. So you undo a few fittings here, and it gives you access to the pump. So the first thing that you need to do is just remove this little panel on the front of the pump. This gives you access to the actual rotor. So when you take that panel off, there's 4 screws on the top of the pump that hold the pump head in place. I've already loosened them off, so you just simply take them and pull them apart. And the entire pump head comes off. You can set that aside for a moment. The diaphragm itself is here. So you can see actually this one's been fairly well used and abused. It's got a little bit of a tear in it, so it needs to be replaced. To get access to the diaphragm, you simply turn the rotor and get the the piston in such a position that it gives you access to the diaphragm, and then you can simply grab it and turn it. It's on a screw. Twist it out like this, and just be a little bit careful because there's some O-rings, not O-rings, but washers underneath it as well, so I can pull it out. There's the washers. Discard the old one, put the new one back in its place. If you see any debris or dirt or anything like that inside the housing, you can clean that out as well. So that's replacing the diaphragm. There's actually a couple of other items that you need to deal with as well inside the pump head itself. So there's another screw right on the top that you can undo that one. And the head is actually in two pieces, so you can take it apart like this, drop the screw on the floor. And this gives you access to these two gaskets right here. So these can be replaced at the same time as well. The diaphragm, the two gaskets inside the head come as a kit that you can keep on hand and do that at least on an annual basis. And then, of course, the whole thing, the head goes back together, you drop the 4 screws back in, and basically you're done. You're back in service. So as I mentioned with the Div 1, it's really not necessary to take it off the rail. You can operate on it while it's sitting on the rail like this. Okay, we'll set that aside. The other thing I wanted to talk about is the cell itself. Now, it's unlikely if your sample conditioning is doing its job that you would need to go into the cell on a regular basis. But if something were to happen where it got flooded somehow, some liquid was able to get into it, the user does have access to the inside of the cell. So to take the cell off, there's basically 4 bolts here that hold the entire assembly down to the rail. You will have to undo the fiber optic cable from the laser launcher. So it just screws out and you can just pull it out. It's keyed, so you can't put it back together wrong. And to manage the fiber, we just simply sort of wrap it around the cell just to keep it from flopping around when we're taking the cell in and out. But it can be just simply removed and gotten out of the way. And then the entire, as long as all the fittings are undone, the entire cell assembly will just lift off just like this. And you can set that aside. I should also mention that there's a electrical connection here from the detector to the main board, so don't go too far without undoing that first. So once you have the cell on the bench, you can operate on it. One thing I found that's really handy if you have a vise or a 90-degree bracket, it's a little more convenient if you can actually put the cell vertically like this, because you're going to have access to these bolts here to take the cell shroud off. In this case here, for the purposes of our demo, I'm just going to do it on the bench. I've already taken most of the bolts out. There's just a couple here. So using an Allen key type of wrench, I can simply undo the bolts. Set those aside. And once I do that, essentially the whole shroud assembly can be pulled off. Be a little bit careful with it. There's a tube that actually extends down into the cell to make sure that we have adequate gas mixing. I don't know if you can see that extended tube inside there, but it may want to rub up against the cell. If this gets dirty, you can just use a paper towel or something to wipe the sides of it down. I'm going to set that aside for the time being. So this, again, gives you access to the cell itself. So you can see this is the optics cage here. There's your far mirror and your near mirror. If anything gets on those mirrors, they're relatively easy to clean. you can just simply use some Kim wipes or some other kind of lint-free wipes. You can use some methanol. Simply wet the wipe and then just simply apply it gently to the mirrors themselves. Give them a good little cleaning. Any debris, dust, that sort of thing should be able to come off. And if you have some compressed air or a can of compressed air, you could do that to just give them a little spritz of air to evaporate off the methanol and to get rid of any dust particles or anything that's on the cell. Once you've done that, you can simply replace the shroud, put the bolts back in, bolt it back to the rail, plug the fiber back in, and then everything's ready to go again at that point. So everything is mechanically fixed, so there's no adjustments that can be done or are necessary to be done. So once you have it all cleaned and put back together, simply put it back in service, let it warm up again, and you're good to go. So those are some of the maintenance procedures and a little bit of a closer look at the internal optics. I'm going to now turn my camera off, and I'm going to share my screen. So the last thing I wanted to show is a little bit of a demonstration of the actual user interface. This is the remote user interface. So to log in, basically you need a web browser, preferably Google Chrome or Firefox. Internet Explorer, we've found out doesn't work very well, but Google Chrome and Firefox are good options. If you have several units on a network, you can basically tag them on your favorites bar here with their specific IP addresses. I've got mine located here. When you type in the IP address, you get the little splash screen. There's a password. Default password is FACT factory. And you jump in and you can see a bunch of the features of the analyzer. So at the top, we have a few items like polling the page, which means basically refreshing any information on the page for pages that don't update live. We have writing commands that allow you to change parameters if necessary. There's a bypass button here that allows you to bypass the outputs. There's also a bypass button on the handheld keypad. You can acknowledge any latched alarms here as well, and also do a firmware upgrade if necessary. So basically along the side here, we can see some information about the analyzer. Here we see the actual concentration readings of the three gases. So in this case, what we're looking at here is just a sample of the utility gas in our building. And you can see the concentrations here, typically about a half a part of H2S right now. It's reading 0.6. We've got about 0.4% of CO2, or 4,300 ppm. And the water vapor tends to hang around in the 40s of ppm. Over here, we can see the cell pressure and cell temperature. So the pressure is in, I think that's in either torr or millimeters of mercury. That correlates to about around 3 point something PSI absolute. And then the cell temperature is at 40 degrees. So these two items here have alarms associated with them. So if the cell pressure gets too high or too low, that can indicate issues with either the pump, or it could indicate issues with the sample flow. If you're, for example, if the probe gets plugged and there's no flow to the analyzer, basically the pump will pull the cell pressure down. So you get a cell pressure low alarm, or if the pump something went wrong with the pump or the vent line became obstructed, you would get a high pressure alarm. So basically what you're looking at here, sometimes you'll see some of the numbers jump around a little bit. I'll just walk you through the sequence of what happens. So when it's sampling H2S, basically H2S and CO2 are analyzed by the same laser. We actually, in this analyzer, have two lasers inside, and they're coupled to the cell through a fiber optic splitter. So when it's measuring H2S, which it is right now, we set the drive current of the laser to it absorb, so it puts out a wavelength that corresponds to an absorbance feature of H2S. And we can do that for a fixed period of time. Typically, we do it for 10 or 20 seconds, and then it jumps down to CO2. And what it just did there to jump to CO2 was it actually changed the drive current of the laser to put out a slightly different wavelength that corresponds to an absorbance feature of CO2. The fortunate thing about H2S and CO2, well, maybe fortunate or unfortunate because they're very close together. There is the potential for them to interfere with each other, but we mitigate that by using that vacuum pump to narrow the lines. But it does allow us to measure both components with a single laser just by simply changing the wavelength. They're actually, the features are within tuning distance on a single laser away. And then when we measure H2O or water vapor, we turn the H2S laser off, we turn the H2O laser on, and that particular laser is tuned to an absorbance feature of H2O, so we can measure H2O. So in this way, we can get a sequential measurement of the three different components. And say we do it based on a 10-second cycle, that gives you basically a 30-second cycle of measurement of the three different components. So you get an update basically every 30 seconds to a minute for all the components. So along the side here, there's several items related to operation. I'll go through them relatively quickly. We have an alarms page, which allows us to view fault alarms, concentration alarms. We have some statuses of various pieces of hardware. If you want to have a look, see what your analog outputs are doing or what relays are active. The global page just has some sort of general information about the analyzer. For example, over here, you can see some of the parameters associated with three different lasers that we're, or three different laser wavelengths that we're using. So you can see how the drive currents can be set. And then down here, we have some things related to purge time, how often we want to sample the different gases. There's a calibration page that allows you to do things like enter the concentration of the gases that you're measuring. The analyzer is actually offered with either one component or any combination of the three. So if you're only interested in H2S and H2O, for example, we would just simply eliminate the CO2 and you would only measure those two components. So you can measure anywhere from 1 to 3. We have some parameters associated with the runs themselves. For example, we can have high and high alarms for each of the components. We can set those up and assign actions to them. The sequencer allows us, if we multi-stream, allows us to sequence how we want to have them run. We also have a scheduler, which allows you to run certain streams or validation runs based on time. So if you wanted to do a validation run, every day at 6 a.m., you could do that. There's some setups for some of the fault alarms, so you can see the different types of alarms we have available. If the I/O board stops communicating with the controller, the laser, for whatever reason, if it can't communicate, if there's basically not enough laser light because the cell became fouled somehow, things like that. So these are the types of fault alarms that you can generate. We have Modbus outputs. If you're familiar with some of our other products, you know that we like to have programmable Modbus lists. Basically, what we do is along this left-hand side here, we give you a pick list of items that are related to the measurement, and we allow you to drag and drop them into the floating points or coils, or however you want to read them. We can also program that Modbus list for you in advance. The archive, basically the archive gives you a running history of the analyzer, showing basically every time it makes a measurement, it logs it. And it's a tremendous amount of information, but it allows you to go back in time many days, so typically about a month back. So it logs things such as which stream ran, if there was any alarms with it, shows you the H2O concentration, the cell pressure, cell temperature, what the CO2 concentration was, and the H2S concentration. So in this way, you can kind of correlate between pressure, temperature, and the readings. A similar thing is the event logger, which shows you different statuses of the analyzer itself on a per run basis. So if there were any alarms active, you'd be able to suss them out here. We have discrete inputs that are available for either discrete alarms like pressure switches and that sort of thing, or they can also be used to initiate runs. Outputs, we have the relay outputs. You can set them to be fail-safe or not. The solenoids as well in a similar way. And then we can also, down at the bottom here, assign the analog outputs with high and low limits. You could also indicate whether or not you want to use the fail-safe value when you put the analyzer into bypass. We also have some analog inputs. These are typically associated with the analyzer, for example, the cell pressure and temperature, things like that. And then there's links to some drawings, user manual, some information about. There's an output test here, which allows you to basically fire your loops if you want to. So for the outputs, you can set out a pre-programmed value, and then you can also do the same thing for your relay outputs at the bottom. And you can fire them. To do that, you need to use this command here called direct board control. Basically, that takes the control away from the analyzer and gives it to the user. Okay, so that's the 5-cent tour through the web browser-based GUI. At this point, I will hand things back over to Ian to wrap things up.
Sure. Before we wrap things up, there's a couple questions that came out. One of which is the laser specific to H2S, or will ethyl and methyl mercaptans be detected or as an interferent?
The laser is in fact specific to H2S. Other sulfur compounds don't have any absorbance features near the one that we're looking at for H2S. Really, the only main concerns in the natural gas world that we have as far as interferences go are from CO2 and methane, simply because they do have absorbance lines that are in the neighborhood of the H2S, and also because they're usually present in concentrations that are so much larger than the H2S that we're looking at. For example, you may have up to 95 or close to 100% of methane in the presence of a few tenths of ppm of H2S. So again, that's the importance of that vacuum pump, to narrow the absorbance lines in order to mitigate those interferences.
Okay. Does the analyzer have to discharge to atmospheric vent?
It does not necessarily have to discharge the atmosphere. We can discharge it to a low pressure flare. We can tolerate up to about 2 or 3 pounds of pressure on the output. Just one thing to bear in mind is that if you're having flare activities where the pressure in the flare line may go up, it can certainly affect well, two things. You want to make sure you have some kind of a mechanism to prevent backflow to the analyzer, so a check valve or something like that. And also, if the pressure in the vent line gets too high, it can affect the readings of the analyzer. Typically, you'll get a false high if there's too much pressure in the vent line.
Okay. The sample pressure, is that PSIA or PSIG?
So the input sample pressure is 10 PSIA, and then the cell itself operates at about, or pardon me, I'll back up. The input pressure to the analyzer is 10 PSIG, so that's gauge pressure. Once it goes through the metering valve and then is drawn out with the pump, the balance between that flow and pump pressure draws the pressure inside the cell down to about 3 PSIA.
Perfect. The cell is self-inerted. What about the sample system?
In this case, it's not, but we certainly offer that as an option. I know different companies have different sort of guidelines surrounding sulfur inert. Personally, for Galvanic, our sort of standard around that is that for any analyzer where we operate below 1 ppm, we will always sulfur inert all the sample system components. Above that, we typically don't, but we certainly can if it's a requirement of the customer.
Okay. Is there any concern that the target trace gas components are absorbed to the membrane filter?
There's always a concern about sample conditioning and maintaining the integrity of your sample. The filter itself, no. There's no concern about losing or absorbing. But when I opened that filter and showed how to change the membrane, you saw that oily stuff in there. And that's what I would be concerned about, is that oily material can certainly cause absorption, especially of H2S. It can absorb into that kind of material, so you can have false lows. The other thing that can happen with that oily type of stuff is that it can absorb, and it can also desorb. If you have a pressure drop or a change in temperature, it can also desorb H2S, so it might show up as also a false positive in your analyzer as well. So that's really the importance of keeping the sample conditioning system free of liquids like that. Is very important to try to eliminate those types of false readings, either high or low, that you can get from your sample conditioning.
Perfect. All right. Thanks, Dave. Obviously, you can see that we have a very, very well-designed analyzer that really doesn't need support. However, if you do want factory support and startup, we have local support on site. We have technicians all over the world that are available to help, as well as factory acceptance tests we can do at the factory. We also have phone support, and if you go to our website, there's also a spot where you can go online and you can actually get in contact with one of our service techs online, basically 24 hours a day, to make sure that you get the questions answered that you want from a service point of view. So if you're looking at the analyzer as a whole, this is a 1-hour presentation, and we really tried to make it and design it to be 1 hour so we didn't take too much of your time, but also because it's such a robust and simple measurement, and the way that we designed it, it really takes 1 hour to show you how easy it is to make this work properly. Really what you're looking at, again, and I've said it before and I'm going to say it again, 3 measurements, 3 compounds, 1 cell, total certainty. It makes sure that the overall architecture is robust, easy to use, and is really reliable and maintenance free in terms of the measurements you need to make in these types of applications. And we really designed this in this way because of our 40 years of natural gas industry expertise. So thank you very much. Please don't hesitate to get in contact with your sales team, whether it's myself or Selwyn or Michael Barnett or Michael Milam, the platform manager, Parisa, who you heard today. Also, Dave is available to help us as well, and our service representatives, as well as any of your local partners. We have representatives and distributors around the world that would love to take your questions and help you out. So thank you very much for your time. We appreciate you taking time out of your day to come and listen to the launch of this analyzer. And as much as anything else, it's a weird time in the world. Please stay safe, stay healthy, and we really appreciate the time that you spent with us today. So thank you. Have a great evening, and we look forward to hearing your feedback. Bye for now.